Nearly a billion miles from Earth, in the frozen depths of our solar system, something impossible is happening. Picture this, a world smaller than the state of Arizona, encased in a shell of ice thicker than the Grand Canyon is deep, orbiting a gas giant where temperatures plunge to minus 200 degrees Celsius. Logic tells us nothing could survive out here. Nothing should be moving. Nothing should be alive. And yet, from the southern pole of this tiny frozen moon, massive jets of water vapor are erupting into space at supersonic speeds, shooting hundreds of miles above the surface. When NASA's Cassini spacecraft first witnessed this phenomenon, it changed everything we thought we knew about where life could exist in our universe. Today, we're diving deep into one of the most astounding discoveries in the history of space exploration. This is the story of Enceladus, Saturn's sixth largest moon, and the hidden ocean that could harbor alien life. Enceladus was first discovered in 1789 by the British astronomer William Herschel, the same man who discovered the planet Uranus just 8 years earlier. Using his handmade 40-foot telescope, Herschel spotted what appeared to be a tiny point of light orbiting Saturn. He named it after the giant Enceladus from Greek mythology, a fitting name for what would turn out to be one of the most dynamic worlds in our solar system. For nearly 2 centuries, Enceladus remained little more than a catalogued object in our astronomical records. Early observations told us it was small, roughly 500 kilometers in diameter, about 1/7 the size of our own moon. Scientists assumed it was just another dead, frozen rock among Saturn's extensive family of over 80 confirmed moons. Everything changed when NASA's Voyager spacecraft flew past Saturn in the early 1980s. Voyager 2's flyby in 1981 captured the first close-up images of Enceladus, and what scientists saw puzzled them immediately. Unlike most moons in the outer solar system, which are covered in ancient craters accumulated over billions of years of cosmic bombardment, Enceladus showed remarkably smooth regions with very few impact craters. This could only mean one thing: something was actively resurfacing this moon, erasing the evidence of ancient impacts. The surface was geologically young, perhaps only a few million years old in some areas. This was extraordinary. For a small moon to maintain geological activity requires energy, and there was no obvious source. Enceladus receives barely 1% of the sunlight that reaches Earth. It has no atmosphere to speak of. It doesn't experience the kind of extreme tidal heating that powers the volcanoes on Jupiter's moon Io, and yet, something was keeping this little world alive. The mystery deepened when astronomers noticed that Enceladus orbits within Saturn's earring, a faint diffuse ring of tiny ice particles that extends from the orbit of Mimas to beyond the orbit of Titan. Calculations showed that these ice particles couldn't maintain stable orbits for long. They would gradually spiral into Saturn or be blown away by radiation pressure. The earring needed a constant supply of fresh material to maintain itself. Where was this material coming from? To understand what makes Enceladus so extraordinary, we need to explore the fundamental physics governing moons in the outer solar system. When we think about habitability and the potential for life, we typically focus on the habitable zone around stars, that Goldilocks region where temperatures allow liquid water to exist on a planet's surface. Earth sits comfortably in our sun's habitable zone. Mars sits at the outer edge. Beyond Mars, we enter regions where sunlight is too weak to maintain surface water. Saturn receives less than 1% of the solar energy that reaches Earth. At that distance, surface temperatures drop to around minus 180 degrees Celsius. Under these conditions, water doesn't just freeze. It becomes as hard as granite and behaves more like bedrock than ice. But here's where physics gets interesting. While surface water cannot exist at these distances, subsurface oceans are theoretically possible if there's an internal heat source. On Earth, our planet's internal heat comes from 2 sources: residual heat from the planet's formation billions of years ago, and radioactive decay of elements in the Earth's mantle and core. Both processes release enormous amounts of energy that keep our planet's interior molten. For small moons like Enceladus, these heat sources are insufficient. Enceladus is too small to have retained significant primordial heat, and too light to contain enough radioactive material to power geological activity. This is where orbital mechanics becomes crucial. Enceladus orbits Saturn at a distance of approximately 238,000 kilometers, completing one orbit every 1.37 Earth days. Its orbit is slightly elliptical, meaning the distance between Enceladus and Saturn varies as the Moon travels along its orbital path. More importantly, Enceladus is locked in what's called an orbital resonance with another of Saturn's moons. Dione. For every orbit Enceladus completes around Saturn, Dione completes exactly half an orbit. This 2-to-1 resonance creates a gravitational tug that prevents Enceladus's orbit from becoming perfectly circular. The elliptical orbit is the key to everything. As Enceladus moves closer to Saturn, the planet's immense gravity pulls harder on the near side of the Moon than the far side. This differential gravitational force, known as tidal force, literally stretches Enceladus into a slightly elongated shape. As the Moon moves farther away in its orbit, the tidal force decreases and Enceladus relaxes back toward a spherical shape. This constant squeezing and relaxing generates friction within the Moon's interior, and friction generates heat. It's the same principle that makes a rubber ball warm up when you repeatedly squeeze it. This process, called tidal heating, is what powers the remarkable activity on Enceladus. The energy generated by this tidal flexing is substantial enough to melt ice deep within the Moon, creating and maintaining a vast subsurface ocean beneath the frozen crust. In July 2004, after a 7-year journey through space, NASA's Cassini spacecraft entered orbit around Saturn, beginning what would become one of the most successful planetary missions in history. Cassini was a technological marvel, carrying 12 scientific instruments designed to study Saturn, its rings, and its moons in unprecedented detail. The spacecraft's primary mission was scheduled to last 4 years, but it would ultimately operate for 13 years, revolutionizing our understanding of the Saturn system. Enceladus wasn't initially a high-priority target. Mission planners were more focused on Titan, Saturn's largest moon, which has a thick atmosphere and lakes of liquid methane on its surface. But everything changed on February 17, 2005, when Cassini made its first close flyby of Enceladus at a distance of 1,264 kilometers above the surface. As the spacecraft passed over the Moon's southern polar region, its instruments detected something completely unexpected: a significant increase in the surrounding magnetic field. This wasn't just any magnetic field variation. It was the signature of charged particles, indicating that Enceladus was somehow releasing material into space. Even more surprising, Cassini's infrared spectrometer detected elevated temperatures near the South Pole. While the rest of Enceladus sat at a frigid -200 degrees Celsius, certain regions near the South Pole registered at -93 degrees Celsius. That's still incredibly cold by Earth standards, but it's more than 100 degrees warmer than it should be. Something was generating significant heat at Enceladus's South Pole. Scientists immediately recognized they had stumbled onto something extraordinary. They redesigned the mission's trajectory to include additional close flybys of Enceladus. On July 14, 2005, Cassini made its second close approach, this time flying just 175 kilometers above the surface. The spacecraft's cameras captured images that would change our understanding of the solar system forever. The photographs revealed 4 distinct linear features at the South Pole, dubbed tiger stripes by the science team. These weren't just surface markings. They were deep fractures in the ice, each about 130 kilometers long and 2 kilometers wide, glowing with infrared heat. More incredibly, from these tiger stripes, massive plumes of water vapor and ice particles were erupting into space. The jets shot material hundreds of kilometers above the surface at speeds exceeding 1,400 kilometers per hour, roughly the speed of a bullet. These weren't small geysers. They were continuous supersonic jets of water vapor mixed with ice crystals, organic compounds, and salts. Cassini's instruments analyzed the composition of these plumes in detail. The water vapor was accompanied by carbon dioxide, methane, molecular nitrogen, and complex organic molecules, including formaldehyde, acetylene, and propane. Most significantly, the plumes contained sodium chloride, common table salt, dissolved in the water. The presence of salt was particularly revealing because it indicated the water had been in contact with a rocky core before being ejected into space. Over the following years, Cassini performed multiple targeted flybys of Enceladus, some passing through the plumes themselves to directly sample the material being ejected from the moon's interior. Each flyby added new layers to our understanding of this remarkable world. In 2008, Cassini flew just 50 kilometers above the surface, so close that the spacecraft actually passed through the densest part of the plume erupting from the tiger stripes. The instruments detected not just water vapor, but actual liquid water droplets that had frozen into ice crystals moments after being expelled from the fractures. This proved that liquid water existed beneath the surface, not just warmed ice. The discovery was monumental. Enceladus harbored a subsurface ocean of liquid water. Further analysis of the plume composition revealed molecular hydrogen, detected during a particularly deep dive through the plumes in October 2015. This discovery was groundbreaking because molecular hydrogen is typically produced by hydrothermal activity, specifically by chemical reactions between hot water and rock. On Earth, hydrothermal vents at the bottom of the ocean support thriving ecosystems completely independent of sunlight. Organisms called chemotrophs harness the chemical energy from compounds like hydrogen sulfide and molecular hydrogen, forming the base of a food chain that includes tube worms, crabs, fish, and countless other species. The detection of hydrogen at Enceladus suggested that similar hydrothermal processes might be occurring on the ocean floor beneath the ice. Using gravity measurements collected during multiple flybys, scientists calculated how Enceladus's mass was distributed internally. The data revealed that beneath the south polar region, there was a significant mass deficit, indicating the presence of a large body of liquid water. Initially, scientists thought this might be a regional sea confined to the south polar area, but in 2015, additional analysis of Cassini's gravity data confirmed that the ocean was global, extending beneath the entire icy shell. This ocean is estimated to be about 10 kilometers deep, sitting beneath an ice crust that varies from 20 to 25 kilometers. Thick in most places but maybe as thin as 5 kilometers, at the South Pole where the tiger stripes allow direct access to the ocean below. The total volume of water in Enceladus's ocean is comparable to some of Earth's largest lakes. The final piece of the puzzle came from studying the ice particles in the plumes. Scientists found that some particles contained complex organic molecules including large carbon-rich compounds. These weren't just simple molecules. They were the building blocks of life as we know it. Combined with the presence of liquid water, chemical energy from hydrothermal activity, and organic compounds, Enceladus met all the basic requirements for habitability. The implications of the Enceladus discoveries extend far beyond a single moon of Saturn. They fundamentally reshape our understanding of where life might exist in the universe. For decades, the search for extraterrestrial life focused primarily on Mars and on planets orbiting other stars within their habitable zones. The assumption was that life required sunlight, either directly for photosynthesis or indirectly to maintain surface temperatures warm enough for liquid water. Enceladus proved that assumption wrong. Here is a world with absolutely no sunlight reaching its ocean, yet it possesses all the ingredients necessary for life: liquid water, organic compounds, and a chemical energy source. This discovery expanded the definition of habitable environments throughout the cosmos. The ocean of Enceladus exists in complete darkness, just like the deep oceans of Earth before photosynthetic organisms evolved. And just like Earth's deep ocean, life on Enceladus would need to derive energy from chemistry rather than light. The detection of molecular hydrogen is particularly significant because it suggests active hydrothermal vents on the ocean floor. On Earth, these vents form where seawater seeps into cracks in the ocean floor, gets heated by magma chambers below, and then erupts back into the ocean loaded with dissolved minerals and gases. The interaction between hot water and rock drives chemical reactions that produce hydrogen, methane, and other compounds. These chemicals represent stored energy, and certain microorganisms have evolved to extract that energy through metabolic processes. If similar processes are occurring on Enceladus, then the conditions for life are not just present but actively maintained. The energy source isn't running out, it's continuously regenerated by tidal heating. This is sustainable habitability over geological timescales. Scientists have modeled the internal structure of Enceladus to understand how this system functions. The Moon consists of a rocky core approximately 190 kilometers in radius, surrounded by the global ocean, which is itself enclosed by the thick ice shell. The tidal flexing of Enceladus generates heat primarily through friction in the ice shell, and at the interface between the rocky core and the ocean. Computer simulations suggest that the ocean floor could have hydrothermal vents similar to those on Earth, with water temperatures near the vents potentially reaching several degrees above freezing. The tiger stripes at the South Pole represent the most direct connection between this hidden ocean and space. The exact mechanism that creates and maintains these fractures is still debated, but the leading theory involves a combination of tidal stresses and heat from below. The ice at the South Pole is under tremendous stress as Enceladus flexes in its orbit. This stress creates fractures that penetrate down to the ocean. Warm water under pressure surges up through these cracks, and as it reaches the surface where pressure drops dramatically, it explosively vaporizes, creating the spectacular plumes we observe. The plumes themselves provide an incredible opportunity for science. Rather than having to drill through kilometers of ice to sample the ocean, we can simply fly a spacecraft through the plumes and collect material directly ejected from the subsurface ocean. It's like the Moon is providing free samples of its most interesting secrets. The scientific community has embraced Enceladus as one of the highest priority targets in the search for extraterrestrial life. Dr. Christopher McKay, a planetary scientist at NASA's Ames Research Center and expert on extremophile life, has stated that if hydrothermal vents exist on Enceladus, then the probability of life existing there is high. He points to Earth's own hydrothermal ecosystems as proof that life can thrive in such environments. Some scientists urge caution, noting that while Enceladus has the ingredients for life, that doesn't guarantee life exists there. Dr. Kate Kraft from Johns Hopkins University emphasizes that we need to understand more about the ocean's chemistry, particularly its pH levels and the concentration of nutrients, before making definitive claims about habitability. There's also debate about how long the ocean has existed. Some models suggest that Enceladus's current activity is a recent phenomenon, perhaps only millions of years old. If that's true, there might not have been sufficient time for life to originate. However, other researchers argue that the tidal heating mechanism could have been active for billions of years, providing ample time for biological processes to begin. The discovery also raises questions about other icy moons in our solar system. If Enceladus can maintain a subsurface ocean, what about Jupiter's moon Europa, or Saturn's moon Titan, or even distant Neptune's moon Triton? The paradigm has shifted from asking where liquid water exists, to asking where it doesn't exist. Each of these worlds now represents a potential habitat for life, dramatically increasing the number of places we need to explore. Perhaps most philosophically significant is what Enceladus tells us about the universe at large. If life can exist in the dark ocean of a small moon orbiting a gas giant, then similar environments could be common throughout the galaxy. Icy moons might be the most abundant habitable environments in the universe, far outnumbering Earth-like planets and their stars, habitable zones. Before we continue exploring what comes next in our investigation of Enceladus, I want to hear from you. If NASA sent a mission to Enceladus tomorrow and confirmed the presence of microbial life in that hidden ocean, how do you think it would change humanity's perspective on our place in the universe? Would it inspire a new era of space exploration, or would it be just another headline that fades from memory? Drop your thoughts in the comments below, and if you're finding this deep dive into Saturn's most mysterious moon as fascinating as I am, make sure to hit that like button. It genuinely helps this content reach more people who are passionate about space exploration and the search for life beyond Earth. Your engagement makes a real difference in supporting this channel's mission to bring you the latest and most exciting discoveries from NASA and space science. The Cassini mission officially ended on September 15, 2017, when the spacecraft deliberately plunged into Saturn's atmosphere, a planned destruction to prevent any possibility of contaminating Enceladus or other potentially habitable moons with Earth microbes. But the science from Cassini continues. Researchers are still analyzing data collected during the mission, extracting new insights from the vast archive of measurements, images, and observations. Currently, multiple mission concepts are being developed specifically to return to Enceladus. NASA's proposed Enceladus Orblander would be a revolutionary mission that combines an orbiter and a lander in a single spacecraft. The orbiter would make multiple passes through the plumes, collecting and analyzing samples with far more sophisticated instruments than Cassini carried. After completing its orbital phase, the spacecraft would attempt to land on the surface near one of the tiger stripes. The lander would use advanced life detection instruments to search for biosignatures in the ice and plume material. Another concept called the Enceladus Life Finder focuses exclusively on detecting life by analyzing organic molecules and looking for specific patterns that indicate biological processes. This mission would carry a mass spectrometer capable of distinguishing between organic molecules created by geological processes and those produced by living organisms. The European Space Agency is also considering an Enceladus mission as part of its long-term exploration program. International collaboration could make a sample return mission feasible, where a spacecraft collects material from the plumes and brings it back to Earth for analysis in laboratories. The technological challenges are significant. Landing on Enceladus would require navigating its plumes and dealing with extremely cold temperatures. Communication delays with Earth mean spacecraft must operate autonomously, and any mission must be meticulously sterilized to avoid contaminating Enceladus with terrestrial life. Despite these challenges, the scientific payoff would be extraordinary. Discovering life on Enceladus would answer one of humanity's most profound questions. Are we alone in the universe? From a forgotten point of light in William Herschel's telescope to one of the most promising locations for extraterrestrial life in our solar system, Enceladus has taken us on an incredible journey of discovery. We've learned that this tiny frozen moon, smaller than the state of Arizona, harbors a global ocean of liquid water beneath its icy shell. We've witnessed spectacular plumes erupting from tiger stripe fractures at the South Pole, shooting water vapor and organic compounds hundreds of miles into space. We've detected molecular hydrogen that hints at hydrothermal vents on the ocean floor, creating environments that could support life even in total darkness. The story of Enceladus reminds us that the universe is far more dynamic and surprising than we ever imagined. It challenges our assumptions about where life can exist and inspires us to keep exploring, keep questioning, and keep pushing the boundaries of human knowledge. If this journey through the mysteries of Enceladus has sparked your curiosity about space exploration and NASA's incredible discoveries, make sure to subscribe to this channel. We're constantly bringing you the latest findings from missions across our solar system and beyond. Hit that notification bell so you don't miss our next deep dive into the cosmos. The universe is full of wonders waiting to be discovered, and we're going to explore them together. Until next time, keep looking up. The information presented in this video is based on actual scientific data and research published by NASA, the European Space Agency, and peer-reviewed scientific journals. The discoveries and observations discussed are real findings from the Cassini-Huygens mission to Saturn, which operated from 2004 to 2017. While we strive for accuracy in presenting scientific findings, space science is a rapidly evolving field, and new discoveries may refine or expand our understanding of Enceladus and its subsurface ocean. This content is produced for educational and entertainment purposes. For the most current scientific information, we recommend consulting NASA's official resources and recent peer-reviewed publications.